Right.
The chapter 8, section 1, chapter 8 in general deals with fundamental theorem calculus and how it deals with integrals. We found antiderivatives, which are the integrals for functions, but that might not always be that easy because depending on the situation of the function, we can have different scenarios that will require us to use different algebraic rules, trigonometric rules, all sorts of different shortcuts that we have to use in other algebra trig courses. In this section, first section, we're going to start looking at developing different types of methods to solve definite integrals. And these are, since they're definite integrals, those are proper integrals. Now, eventually, we'll look at the domain when the domain and the range go to infinity. Those we call improper integrals because in those situations we have to put a plus c at the end instead of just solving the equation for a solid answer. All right, so let's go ahead and look at these. Oh, I will send you all this chart also. This is a very important table because what it does, this shows us all the shortcuts we can do for the integrals. For example, if we have the integral of sine, I might just jump into negative cosine plus c. These are all indefinite integrals because they have no bounds. The hyperbolic, the inverse, the integral of hyperbolic sine is a hyperbolic cosine. Or the inverse of cotangent is the natural log of sine x. So these are all just shortcuts we'll be using in when we can. So we have to eventually try to get our functions to look like this part and the integrals, and then we just automatically jump in here are the integrals. It'll get more difficult on these right here to find the inverse functions. Using substitution is going to help us use this table. So that's going to be most of the time predominant way we're going to solve these things. And so we're going to use the substitution method. We're going to use the algebraic, the trigonometric identities, the trigonometric shortcuts. So let's look at this thing. The first one, evaluate this integral. Let me write it down on my piece of paper here. Example 1. Evaluate the integral from 3 to 5 of 2x minus 3 over the square root of x squared minus 3x plus 1 dx. All right. So the first thing we do is we're going to apply the substitution rule. So we're going to look at this. We're going to define that as u. Minus 3x plus 1. Now we take the derivative of that. We get 2x minus 3, which is going to help us a lot because we see that the numerator, we have the form du, in this case, the square root of u. All right, so now since we converted this function to du over u, a square root of u, we can also change the bounds of integration by using this formula here. So when x equals 3, so u of 3, we have 3 squared minus 3 times 3 plus 1. So it's 9 minus 9 plus 1. So now we're going to go from the bound of 1. And for the upper bound, when x is 5, 5 squared minus 15 plus 1. 25 minus 15 plus 1 is 10 plus 1, 11. All right. So now we can just keep it in the functions of u. If we're going to eventually go back, then we have to keep it with respect to, if we're going to do it with x, then we have to do it with the bounds 3 to 5. But now we're going to do it only with respect to du, so we have to transform the bounds from u to x to u. So now we have to look at this integral. This is u to the power negative 1/2 du. The integral of u to the power 1/2 is 1/2 plus 1 divided by 1/2 plus 1. Going from 1 to 11. So what does this give us? Well, this is negative 1/2. So that gives us u to the power 1/2 over 1/2. That one reciprocates. So we have that. Now inside here, we can go ahead and plug in our bounds. We have 2 square root of 11 minus square root of 1 equals 2 square root of 11 minus 2. Square root of 1 is 1. So whatever this value equals, that's our solution. Okay, so that's just going straight forward and doing it as we normally would. All right, so let's go. We may need to use an algebraic technique like complete the square to make it fit. All right, so let's look at this example. Okay, example 2. Complete the square to evaluate the integral of dx radical 8x minus x squared. All right, so here we're going to have to use to complete the square. Why? Because we want to try to make this into a perfect square. So we have 8x minus x squared. Rewriting this because it's quadratic. Right? To complete the square in algebra, we have to make sure that the leading coefficient is positive 1. So we factor out the negative. We get that. All right. Okay. What we have to do now is complete the square, take the b term, take the b divided by 2 and square it. Since we added it wasn't there before we added it, we also have to subtract it. Because we can't change the equation, just change the way it looks. So we have negative x squared minus 8x plus 4 squared, and work this one all the way out. 8 over 2 is 4. It makes it 16. Because this, and we have to distribute that negative sign over there, which becomes a plus. Because now I just want to, this is the complete the square part. So what this gives us is negative whatever's under the squared. So we have x and 4 and whatever the first sign is, plus 16. So that's to complete the square. We do it all on one side. Okay, let's move the 16 in front. The reason we're moving the 16 in front is because our table is usually in the form of a squared plus or minus u squared. Okay, so this is what we're going to have to look at. What is our a squared? Well, a is this. What makes, if a squared is 16, then a is 4. All right. So what else do we have here? And then this. So this is our a squared. And this is our u squared. Our u is x minus 4. Okay, so all of this goes inside there. So we have originally, this brings us down to, we have the integral of du is the square root of a squared minus u squared. So what do we have to do here? Remember, all we're doing here, we have to try is complete the square, because we have to get it into this form. So let's go back to the table and find where we have dx over square root of a squared minus u squared. A squared minus u squared is number 18. So that becomes the inverse sine of u over a. So this becomes the inverse sine of u over a plus c. So plug everything back. We have the inverse of sine. U we defined was x minus 4 over a. A is 4. And there we have our answer. Right? So again, this is the hardest part, because we know we have to use complete the square because it's quadratic in form. We have x squared and 8x, so we complete the square. And there's nothing on top, so that's a good sign. Let's look at example 3. We can sometimes rewrite the integral using equivalent trigonometric expression to get a simple substitution. Right? So this one down, we have example 3. Evaluate cosine of x sine 2x plus sine x cosine 2x dx. All right. As I said, we can use some trigonometric expansions. What we have here is the sum rule of the sine, because sine a plus b is cosine a sine b plus sine a cosine b. That's the trigonometric substitution. Again, it's on the cheat sheets. So we can rewrite this integral as the sine of x. It's the first one plus the second one is x plus 2x. Well, the integral of x plus 2x is sine of 3x. Now, we use substitution, so we say that our u is our 3x, our du is 3 dx. So we need to have a 3 in front of here, so we have to divide by a 3 out here. So we have 1/3. Now the integral of sine is negative cosine plus c. So we're taking the integral of sine of u, which is negative cosine of u. So our answer is negative 1/3 cosine 3x plus c. All right. Let's look at example 4. What is its condition? We'll sometimes need to multiply the top and bottom by the conjugate. In other words, we'll have a function that is integrable or differentiable, but not in its present form. Especially if we plug in what we have at what is pi over 4. So we have the sine of 0 is 0. Sine of pi over 4 is radical 2 over 2. So let's go ahead and solve this. To integrate it, is from 0 to pi over 4 dx 1 minus sine x. So what we have to do here first is multiply by the conjugate of the denominator. So we have 1 over 1 minus sine x. That's the original one. The conjugate is just change the sign in between there. Dx. Now we go ahead and FOIL or multiply together. 1 times that. On the top, we have 1 plus sine x. And on the bottom, we have to 1 times 1 is 1. Positive sine x, negative sine x cancel. Negative sine squared x dx. But now, the question you're going to probably have is, how do we know we have to do the conjugate? Well, we have nothing on top, and on the bottom, we have an equation that's a plus or minus. We can't split it up, and so we have to try to make it into one function. Because what is 1 minus sine squared? Remember, a squared plus b squared equals c squared. The trig identity, it says that cosine squared x plus sine squared x equals 1. I'll move the sine over, then cosine squared x equals 1 minus sine squared x. So this is equal to 1 plus sine x over cosine squared x. So what do we do with that? Because we have an equation on top and a monomial on the bottom, we can split them up. Remember, we're still going for the bounds from 0 to pi over 4. 1 over cosine squared is secant squared plus what we have here, we have sine over cosine squared, which is sine over cosine times 1 over cosine. Sine over cosine is tangent. 1 over cosine is secant. All right. Now we can go back to the table and see if we have this, the integral of this anywhere. All right. So secant squared plus tangent secant. Secant squared plus tangent secant. Okay. So we don't have that equation. So what we can do then is split them up. Secant squared dx plus secant tangent dx. And look for those separately. So secant squared is tangent x. We don't put the plus c because we have a definite integral from 0 to pi over 4. So we don't have to do a plus c. And then secant tangent is secant. From 0 to pi over 4. So the integral of secant squared is tangent. The integral of secant tangent is secant. And we're going for the pi over 4. So we get tangent pi over 4 plus secant pi over 4 minus tangent of 0 plus secant of 0. Tangent of pi over 4 is sine over cosine pi over 4 is 1. Secant pi over 4, that's square root, that's 1 over cosine. Cosine pi over 4 is square root of 2 minus tangent of 0, sine of 0 is 0, so it's 0. 1 over cosine of 0 is 1. We have 1. So we have tangent pi over 4 is 1. Secant pi over 4 is radical 2. Tangent of 0 is 0. Secant of 0. So we have 1 plus radical 2 minus 0 minus 1. The 1's cancel. So our answer is radical 2. Okay. So again, all we're doing is a lot of trig and algebra rules. That was example 4, I believe. Yes. So now let's do number 5. Sometimes we need to use simple long division to solve our simplify our integral. Again, now, when do you do it? When do you use this? Well, let's look at this. We have 3x squared 7x over 3x plus 2x, or just 2 dx. Basically, is when it's a infinite rational expression. As x goes to infinity, if the top degree is larger than the bottom degree, then we will usually go to do the long division. All right, so let's look. Let's go back here and write it down. So in our example here, we have to do here is do the long division, 3x plus 2, 3x squared minus 7x. What times 3x gives me 3x squared? It's x. X times 3x is 3x squared. X times positive 2 is positive 2x. Change the signs. So those cancel. Negative 7, negative 2 is negative 9x. What times 3x gives me negative 9x? Negative 3. So negative 3 times 3 is negative 9x. Negative 3 times 2 is negative 6. Change the signs. And there's our remainder. So what we've just done, we have taken this rational expression and converted it into this. This becomes x minus 3 plus 6 over the denominator, 3x plus 2 dx. All right, so now we could do those in parts. The integral of x is x squared. Integral of 3 is 3x plus, we could use substitution here. So this is u, du is 3. 6 is made up of 2 times 3. So we can take the 2 and put it out in front. So now we have 3 over 3x plus 2, which is the ln function. Since 3x plus 2, if x is negative, can give us a negative answer, we put in absolute values. Then plus c. So here's our solution, our integral. All right, that is number 5. What does this one tell us? Reducing an improper fraction by long division does not always lead us to an expression that's easily integrable. So now we have to look at separating the integrand, the top function. So what do we have here? Okay, so I have, this is example 6. Example 6, the integral of 3x plus 2 over radical 1 minus x squared dx. What we're saying here is we can take, since the top is an equation and we have a monomial on the bottom, we can look at splitting up this equation. So taking by parts. So let's look at the first part. Let's look at this one first. We can use substitution here. Whatever's inside the radical is our u. Du is negative 2x. So the 3 has to go out in front. So what is x? So this is du is 2x dx. We have to solve for x now. We have to get rid of the -2, so divide by -2, -2 both sides. So -1/2 du is equal to x dx. And that's what that is. So with this substitution, what do we get? We took the 3 out in front. X dx is -1/2 du over the radical u, because that's what our denominator is. So that becomes -3/2 integral du over, convert this to u to the power 1/2, which becomes -3/2 u to the power -1/2. When we integrate this, -3/2, u, add 1 to the top, -1/2 plus 1. So we flip that. We get -3/2 times 2/1 u to the power 1/2 plus c. So it equals -3 u to the 1/2 plus c, which is -3 square root of u is 1 minus x squared plus c. So that's the first part. And we can combine these a little later. Now we're going to look at the second part. In the second part, this is part 2. We have the integral of 2 over radical 1 minus x squared. What do we do here? So the 2 is a constant. It goes out in front. Well, yeah, let's look at that. So the 2 is, because if we did that, then we just have dx over square root of 1 minus, and u is 1 minus x squared. Du is 2x. Nope, we can't do that. It's not going to be an ln function because we're missing an x on top. So let's go and look at what we have. What we have in the form dx square root ax minus u squared. Let's see what we have in that terms. Okay, so we want square root of a squared minus u squared. That's going to be inverse of sine by rule 18. So what that tells us is that this whole integral becomes the inverse of sine x plus c. And this is our second part. So combining the two, we got -3 radical 1 minus x squared plus this one, which is 2 inverse sine of x plus c. And there's our answer. Yeah. Example 7. The question of what to substitute for an integral is not always quite clear. That's true. Sometimes we simply proceed by trial and error, and if nothing works out, we try another method. And that could take some time. That's where it gets frustrating. The next sections, we're going to look at new methods. But the substitution works in this coming example because it looks like it's already in the form that we're looking at. Okay, yeah. That's example 6. I need another piece of paper. So example 7 says evaluate this function. Dx over the square root of 1 plus radical x. Oops. And the whole thing is cubed. Whoa, okay, I miswrote that. It's the integral of dx in parentheses 1 plus radical x cubed. So typically we want the inside. So we're going to use substitution. We're going to use 1 plus radical x to be the du, or the u. So du, the derivative is, that goes to 0. This is x to the power 1/2. So it's 1/2 x to the power negative 1/2, which is 1 over 2 radical x. Okay, so that's u du. But on top, we have a dx. Remember, when we take the derivative of u, we always have to put a dx behind it. So, I'm trying to make it back over here. So I'm using this as my u, the 1 plus radical x. The derivative of that is the 1 goes to 0. The derivative of x to the power 1/2 is 1/2 x to the power negative 1/2 dx. We need to have a dx for the top. We have to figure out what that's going to be. So we know that du equals that. Multiply both sides by 2 radical x du. This is a u. No, radical x equals dx. But we need to have x in terms of u. So we go back up here. We have to get x in terms of u. Or we could do radical x even. Radical x is u minus 1. So we do 2u minus 1 du equals dx. So we have the integral. Dx is 2u minus 1 over u cubed du. On top, we could distribute. We got 2u minus 2. We have a monomial on the bottom, so we can split those up. 2u u cubed minus 2u cubed du, which equals, the u cancel, so we have the integral of 2 over u squared minus 2 over u cubed du. Now we take both of these separately. So the integral of this one, bring it on top, negative 2 plus 1. So we have we have u to the power negative 2 plus 1 divided by negative 2 plus 1 minus 2 u to the power negative 3 plus 1 plus c. Then we have 2 negative 2 plus 1 over negative 2 plus 1 minus 2, because we're doing the integral, so we have to add the plus 1. So this becomes 2u negative 1 over negative 1, u negative 2 over negative 2. So this makes the whole thing negative over u minus, no, the 2 of the 2 cancel. So the negative becomes a plus. So it's a 1 on top over u squared plus c. Now substitute back what we had. So we have negative 2 over u. U was 1 plus radical x. 1 plus radical x squared plus c. And there's your answer. All right, let's look at, that's the last one. When evaluating integral, the property of integrand may help us in calculating the result. This one is pretty interesting. Example 8. This is another definite integral because we have bounds. Negative pi over 2 to pi over 2. X cubed cosine x dx. All right. We don't have a direct way, as of yet, we don't have a way of integrating this product because we can't use u du because there's nothing that satisfies the conditions. So what we have to do here is look at the concepts of the functions themselves. X cubed is an odd function. This is an odd. What does that mean? That means if I put, let's say, if I put a positive 1 inside there, 1 cubed is 1. If I put a negative 1 in there, I get a negative 1. So when x is positive, the answer is positive. When x is negative, the answer is negative. That makes it an odd function. Cosine, on the other hand, at cosine of zero, it's 1. And the cosine of pi is also not 1. It's 1. This one's negative 1. So this is an even function. I can't use that. I have to use, so let's look at pi over 4 and negative pi over 4. So the cosine of negative pi over 4, or positive pi over 4, and the cosine of negative pi over 4, they both equal radical 2 over 2. Because if you think about it in the unit circle, pi over 4 is here, pi over 4 is here. Now it gives us negative answers. Pi over 4 and 3 pi over 4 will give us the same values. Yeah, that's how I prove it positive. But it is positive because if on the top half they're both the same, on the bottom half they're both the same at those angles. So now, since we have an odd function and an even function, the product of which will always be an odd function. All right, so that is the first thing. So if it's an odd function, what that means is if I change the signs, I change the numbers. And if I added these two together, I get 0. Because this is symmetric about negative pi over 2 and pi over 2, it's kind of like what we had earlier. We had the semicircle. This half of the circle and this half of the circle are the same. But this side's of the negative, this side's of the positive. But that's what we're going to do here. We just use the properties that since this, we can divide this in half. It goes from 0 to pi over 2, and then from negative pi over 2 to 0. Let's say this is going to give us a positive 1, and this is going to give us a negative 1. So the answer is going to be 0. Because it's going to be an odd function, and the sum of the two differences is going to give you. So the answer of this one is automatically going to be 0. I mean, it's pretty, it's that you have to be able to see that is that when we have a product, first look at what kind of functions each of the products are. If they're both even, then we're not going to have any luck there. But since one's positive, one's negative, and this is a completely symmetrical graph, then we know it has to cancel out. All right, that's it for today. I gotta get ready.